Good morning. Do you hear me well?
Good morning, yes.
Okay, so I need to upload the solutions. I didn't make them in digital format. So I will try to photograph the solution and then upload it on Moodle and then discuss the last time problems, okay?
Sure.
Okay, so I'll come back in two minutes. Okay, I've uploaded the solution. Let me share it with you. So I guess you see my screen now, okay? So maybe we start with 3, okay?
Sure.
I think that was the problem last time, yeah? I also put another solution, a better explained solution for the second exercise, but I think this was already clear from last time. But let's go to 3. Okay. So here, so in 3, what was the problem with 3? So in 3, we wanted to show that the VC dimension of Boolean conjunction is D. So we first shown in the third at the third point that HD conjunction shatters the set of unit vectors, and I think that was clear. Okay. Do you want me to go over again on this part?
If you could.
Okay. Okay, so let's start from scratch here. So exercise 3. So we want to show that the class of Boolean conjunctions. So we want to compute the VC dimension of the class of Boolean conjunctions over the variables x1, x2, xd. So this means that this is the class of all functions from the Boolean d-dimensional cube. So you have arguments that are vectors from 0, 1 in d dimensions, and they are mapped to either label 0 or label 1, and each function has the form of a conjunction where each term it's a literal of variable xi, and could have basically 3 forms. L of xi could be xi, this is a positive literal, the negation of xi, which is the negative literal, or it could miss, it could be missing. So this basically will mean that the conjunction it's the literal, it's always 1 in the conjunction. And we also said that we will consider H minus the member of HD conj, such that H minus will assign to every d-dimensional 0, 1 vector the value 0 always. So with this in mind, so we see that the class of conjunctions will be basically, so each function is a conjunction of d literals, and each literals could take 3 values: positive literal, negative literal, or 1. So this will mean that you have 3 to the power d functions. And we also add the other one, this h minus, which will have the 0 value always. So in total, we show here that the class of Boolean conjunction is finite, and the number of functions in this class is 3 to the power d plus 1. If it's finite, we know from the theory that it will be Pack learnable, and the BC dimension of this class, it's upper bounded by the floor of the logarithm base 2 of the number of terms. So it's floor of logarithm base 2 of 3 to the power d plus 1. And now in the third part of the exercise, we want to show that this class of functions will shatter the set of unit vectors, and because there are d unit vectors, so we will show that the VC dimension is at least d. because you know that the VC dimension is the maximum size of a set C of the so of a subset C of the domain X. Here the domain X is 0, 1 to the power of D. And so is the max. So the VC dimension is the maximum size of a subset C. And because we're gonna show in point C that you have a subset C of D elements, then it will result that the VC dimension of HD con is at least D. And in the last point, the hardest point, we will show that our H cannot shatter any set of D plus 1 points. So this will mean that the VC dimension will be exactly D. So we take C to be the set of all the unit vectors. So this basically will mean that C equals E1 into ED, and each EI is the vector 0 and has only one component equal to 1 on the I component. And we now want to prove that our HD of conjunction will shatter DC. This means that for each possible labeling Y1, Y2, YD of the vectors E1, E2, ED, you will have a function that will make this labeling possible. So this means that for each possible labeling, there will exist an H, a member of all class, such that H of EI will be YY. This will mean that all possible 2 to the power D labeling will be possible. So you'll have 2 to the power D function in H that will map E1, E2, ED in all the possible choices 0, 1 in D dimensions. Okay, so let's see how we're gonna construct for each labeling an H. So we'll consider a random labeling Y1, Y2, YD, and we take G to be the set of indices J for which the label of the J element EG should be 1. So we consider J the set of all indices small j such that Y of J it's 1. Now there are 3 cases. So if J is the empty set, this means that all points E1, E2, ED should be mapped into 0, 0, 0, and this can be made possible by using H minus that we added in our H. So this was the reason for considering H minus in the set of all possible conjunctions with the variables. So this is fine. Now, if we have J to be the entire set of indices from 1 to D, then this basically means that you want to have a conjunction, a function in HD conj that will map every point in label 1, and this is basically the conjunction that has all the literals equals to 1, and this conjunction is called H empty. So all literals are missing, and basically you have a function that no matter what is the point X that it's its input, it will always output value 1. Okay, and now the third case where you have that J it's not the empty set or it's and it's not the entire set 1 to D. In this case, you will define a very particular H that will depend on this set of indices capital J. It will be defined as the conjunctions of all the literal negation of X J small, where J is not in capital J. So it's in 1 to D minus J. So if you consider, for example, D equals 6, so you have 6 dimensions, and capital G to be the indices 1, 2, and 4, then the corresponding function that will map the points E1, E2, E4 in label 1 and E3, E5, and E6 into label 0 will be Hg, the conjunction of x3 negation and x5 negation and x6 negation. And if you check that this function will label E1 into E4 in label 1, you'll have that, for example, for E1, you'll have E1 is 1, 0, 0, 0, 0, 0, so it has component 1 equals to 1 and all the other components 0. So if you apply your function, you'll have it's a conjunction of the negation of the third, fifth, and sixth components. So you'll have 0 negation and 0 negation and 0 negation. You'll have 1 and 1 and 1 that will equal 1. And basically, so if based on the particular form of your function, you will have one value for all the unit vectors that don't have the indices in the capital J set. So here because Hj equals x3 negation and x5 negation and x6 negations, so you'll have that the points x1, x2, and x4 will be back to 1, and the points x3, x5, x6 will be back to 0. Yeah, because for example, if you have Aj applied to the unit vector 3, so to E3, you'll have one negation, which is 0, and something else, so this will be 0. Okay, so using this proof, so we have proved that each ej that is mapped that has the indices in capital J will be mapped to label 1, and each ej with small g which is not in capital J will be mapped to 0. So basically, to each subset capital G of 1 to D, you can have the corresponding labeling that will take value 1 for all the points in J and will take value 0 for all the for all these indices in J. You'll have points from C having label 1, and for all the indices that are not in J, you'll have all the points in C will be back to 0. This basically means that you can generate every subset of C. So you have 2 to the power d functions that are different on C, and this will prove that HD conj will shatter set C, and you'll have that the VC dimension of our H it's at least D. Okay, so this was the first part. Is it clear, this part?
Yeah, it's clear. It's okay.
Okay, now we move to the hardest part, and for which last time I didn't provide such a very nice proof. It is not very explicit. I stayed last night and write the proof like in half an hour, and I think now it is much better explained. So let's go over our proof. So now we want to show that the VC dimension of our H it's strictly smaller than D plus 1. So we will assume that there exists a set C containing D plus 1 points, C1, C2, C, D plus 1. These points are in our D dimensional cube. So each point is a D. It's a vector of D length and has all the coordinates 0 or 1. So we assume that this set C is shattered by our HD conj. So HD conj restricted to the class C will contain all possible functions from C to 0, 1. So now because C has D plus 1 elements, so the number of possible functions will be 2 to the power D plus 1. So so C1, you have C1, it's a member of capital C. So this means that C1 will have D components, and each component it's in 0, 1. So I put here that Ci is in 0, 1 D. So this means that Ci has components Ci1, Ci2, Cid, and each component it's in 0, 1. Okay. Now, so we want to find the contradiction and show that HD conj doesn't shatter any set C of D plus 1 points. now, so if this will happen, so if our class H will shatter C, then among so there it's among then among among the two to the power d plus 1 function H, we will have the following d plus 1 functions. So we will have some particular d plus 1 functions. So you will have H1, you will consider H1, H2, and HD d plus 1 that will map points C1, C2, CD plus 1 into labels, into different labels, and these labels will be the following. So H1 will map all the points to 1, and only C1 will map it to 0. So basically H1 will realize the label 0, 1, 1, 1. H2 will realize the label 1, 0, 1, 1, 1. H3 will realize the label 1, 1, 0, 1, 1, 1. And HD plus 1 will realize the label, the first D points will be back to 1, and the last point will be mapped to 0. Okay, so now you have to take to understand that. So each function gets a point from D dimension. This is a point from a capital C, and will map it to label 0 or 1. And you have, so so each function will realizes a D plus 1 vector of labels. So Hi will map the point C1, C2, CD plus 1 in the vector 1, 1, 1, 1, and there is a 0 labeling on the I component. Okay. So here I said, so Hi with I from 1 to D plus 1 will realize the labels 1, 1, 1 and 0 on the I component, and this can be easily be written of, so you can easily write it Hi applied to the point C, J, it's 1 if E is different than J, and takes value 0 if I equals J. Okay, so we will use the function H1, H2, HD plus 1 to arrive at a contradiction. Now, because each Hi is a member of your class, so it's a conjunction that uses the variables. So this means that Hi can be written as a conjunction of literals, where each literal from that appears in the writing of Hi can have 3 values, and these values, so these values can be for variable xk, so the literal I. So for Hi, we denote all the literals that appear in his writing with Li. So you'll have that each literal from Hi for a variable xk can take the 3 possible values that appear in the definition of our class. So it can take the value xk to be a positive literal negation of xk. So this will be a negative literal, and 1, this will basically mean a missing literal, a literal that will take basically always value 1, and basically will not appear in the writing of Hi. Okay, so I put here an example. So if we consider D equals 3, so a possible member H from H3 conj will be, so could be H equals x1 and the negation of x2, so x1 and x2 negated. So this will mean that, so you can write H as literal of x1 and literal of x2 and literal of x3, and literal only of x1 will be x1, the literal of x2 will be negation of x2, and the literal x3, because it's is missing, has value 1. Okay, so you have all H's in your H class can be written as a conjunction of D literals, and each literal has the form for the variable xk. It can be positive, negative, or missing. Okay, so now for the general case, you have that Hi applied to the vector x1, x2, xd. So you can see x1, x2, xd as variable x1, x2, xd. So HI can be written as a conjunction of the literals, and each literals is of the form Li applied to the variable xk, where of course Li of xk can take only three values: xk, negation of xk, and 1. Okay, so you can have a positive, negative, or a missing literal. Okay, is it clear until now?
Yes, I was thinking that the H function could be basically written as a translation from one literal to another literal. Like, for example, like go up until you define the H's, H1 and H2.
Yeah, you can also be like this. Yeah, I don't know how much it will help it in our proof.
Okay.
So we will see the proof and maybe come back to your idea. Okay.
Sure.
Okay. So on the general case, you have this expression. So now we go back to our h1, h2, and d plus 1. So you'll have that h1 realizes the label 0, 1, 1, 1, 1 on the subset C of 0, 1, d. So C consists of C1, C2, CD plus 1 point. So you have C1 is a point with D dimension, C2 is a point in D dimension, CD plus 1 is a point with D dimension. So each point C1, C2, CD plus 1 will be a vector with D components. Okay, so now you have H1 realizes 0, 1, 1, 1, H2 will realize the label 1, 0, 1, 1, and HD plus 1 will realize the label 1, 1, and the final point will have the label 0. So we will use these labels. So what I wrote here, we will use the label 0 that appear in here to come up with a contradiction. So now if you look very closely to the first row, you see that H1 will map C1 to label 0 and will map all other points C2,
label
C3, CD plus 1 in label 1. Okay, so this means, so if H1 map the point C1 into label 0, because H1, so you now write C1 as the vector C1, 1, C1, 2, C1, D. And this can be written, so H1 is from the general form, it's a conjunction of the D literals L1, L2, LD applied to the variable x1, x2, xd, which for the point C1, x1 it will be replaced by the first component C11, x2 will be replaced by C12, and xd will be replaced by C1d. Okay, so in the end you have that H1 applied to C1, it's 0, and H1 applies to C1 is the conjunction of L1 C11 and L1 C12 and so on. And because you have a conjunction which will result in the 0 label, so this will result that there is at least one literal that will be 0. So you would have, so there will exist an indices K1 from 1 to D such that L1 applied to the component K1 of your point. So basically the component corresponding to the variable xk1 will be 0. Okay, so this will be essential. So you'll have at least one member in the conjunction will be 0. So you apply the same stuff for H2, you apply the same stuff for HD plus 1. So now you have that L1, so L1, the first literal corresponding to H1, on the K1 position will take value 0, on the position K2 will take value 0, and the position D plus 1 will take value 0 because you have D plus 1 functions. So you have D plus 1 function, and you will have D plus 1 literals which have value 0, but these literals, they only use variables either in position 1, position 2, or position D. So you will have that there are at least two literals which will use variables from the same position. Okay, so this is the again another important thing in this proof. So because L1 will get value 0 for xk1 equals so it will be the k1 component of C1. So L1 will have value 0 for the variable on position k1. L2 will have value 0 for the position for the variable on position k2. LD plus 1 will have the value 0 for the variable on position kd d plus 1. So you will have d plus 1 variables, but there are at most d possible variables that can be different. So you'll have two position k1, k2, kd plus 1 that will be equal. Okay, so we have d plus 1 literals that use variables x1, x2, xd. So there are at least two literals using the same variable, and we will denote this variable, these two literals with li and lj, and we will denote the same variable xk. Okay, so this will mean that li will use xk and this will be 0, and lj will use xk and this will be 0 for the points ci and cj. So if I look here, so you have that hi, which is the li applied to variable x1, and li applied to x2, and li applied to xk. So this will be 0 for the point ci, and in the writing of aj, you'll have also the literal lj applied to xk. Okay, and what is important is that this literal cannot be missing. So they cannot have value 1 because let's see. So we're gonna use li and lj to arrive at a contradiction. So we know that li and lj will satisfy the following conditions. So li apply to the point to the variable xk for the point ci will be basically li applied to the k component of the point ci. So this will take value 0 because we said that hi applied to the point ci equals 0, and this is due to the fact that we have that there exists a literal, and we call this literal li on the k component that will be 0. Okay, so we have and the conjunction, okay, and the conjunction contains the literal li cik, which is 0. So you'll have that li applied to cik is 0, and also the same stuff, you'll have that lj applied to cjk equals 0. And this, so from the previous stuff, we saw that if li and lj are 0 and they use the same variable on the position k. Okay, so you'll have that la for the point cik, it's for the component ci, the k component will be 0, and lj will have the value 0 for the cj point on the component k. Okay, so do you understand until now? Because it is very technical, and I'll do very small steps.
Yeah, I got lost at the k index. I mean, when we have ly of c.
Okay, so let's go back. So you'll have that. So you have d plus 1 function. Okay.
Mm-hmm. Yeah.
Okay. So d plus 1 functions, and each function will have value 0 in one point. So this will mean that in the expression of each h, you will have a literal that will get value 0.
Yeah.
Okay. Now, because you have d plus 1 functions, you'll have for each function, you'll have a literal that have value 0. So you'll have d plus 1 literals that have value 0. And the idea here that each literal can have value 0 either on the position 1 for x1, either on the position 2, either on the position 3, either on the position d. Okay.
Okay, okay.
So if you have like D equals 3, as in the previous example here, yeah? So
Yeah.
you can have either an H will have either a literal, will have either a literal that uses x1, x2, and x3, okay?
Mm-hmm.
Now,
Yeah.
because you have D plus 1 function, you have H1, H2, H3, and H4. So in each H, you'll have either, so in each H1, you'll have L1 of x1, L1 of x2, or L1 of x3 will be 0. Okay?
All right, I got it.
In H2, you'll have L2 of x1, L2 of x2, and so on. So in the end, you'll have two literals that appear in the writing of HI and HJ that they will use the same variable xk.
All right.
Okay?
Mm-hmm. Yeah.
Okay, so here you see, so you have in HI, you have the literal Li that is using xk, and in HJ you have the literal Lj that is using the variable xk. And the most important thing is that these literals have value 0 for the particular points when HI is applied to the point Ci. So when you replace xk with the k component or the vector Ci, this will be 0. And Lj of xk will be 0 when you replace xk with the k component of the vector Cj. Okay?
Yes.
So this will mean that these literals cannot take value 1. So in the beginning, you saw that each literal can take value xk, negation, or 1. But now you can see that this cannot take value 1 because for some values they will take value 0. So for Cik it will take value 0. So this means that Li cannot be literal 1, the missing literal, and Lj will take value 0 for Cjk. So this will mean that Lj cannot take value 1. So I put here, so in general you have that each literal can take 3 values, but because Li of Cik equals 0, this means that Li is different than 1. So each literal can take either xk or negation of xk. Okay?
Okay, yeah.
Okay. And now, so we arrived at this point. So now we have 4 possible cases, and we are very close to our final argument. So you have four possible cases. So the first case, Li of xk is xk and is the same with Lj of xk. So this basically will mean that Hi of Ci will be a conjunctions where Li of Cik will be replaced basically by Cik, because Li will map the variable xk to xk. So if you have that Li of Cik equal 0, this will mean that the k component of the vector Ci is 0. Okay? But if you apply Hj to the point Ci, you know that Hi applied to Ci is 0, because this is how Hy was defined, and Hj applied to Ci it's 1 because E is different than J. Yeah. So each Hi will realize the labeling 1 1 1, and you have 0 on the position I. So this will basically mean that Hi will map each point to label 1, and only will map point Ci in label 0. So Hi of Ci is 0, and you'll have that the literal Li on the position K will be 0. So you'll have that Li applied to Cik it's 0. So in this case, Li of Cik will be equal to Xik. So the key component of the vector Ci is 0. And now if you apply Hj to the point Ci, you'll have the value will be 1. So in the conjunction of Hj, you know that there is this Lj. Now Lj on the position xk, it's xk, but now xk, so this should be 1. So because the entire result of your conjunction is 1, it means that all terms in the conjunction are 1. So if all terms in the conjunction are 1, this means that Lj of Cik will be 1. But you know that Lj, so Lj of Cik, it's 0 because Lj of Cik in the form of, or on this particular case, because Lj will map the variable xk into xk, so you'll have that Lj will map the point the component Cik into Cik. So this will be 0, and this is the contradiction that you arrive at. On one hand, you'll have that Cik should be 0, and on the other hand, you'll have that Cik will be 1. Okay.
Yep, got it.
Okay, and then you will use the same argument for case 2, case 3, and case 4. So for case 2, you'll have that instead of, you'll have the other case that Le will map is xk in the negation of xk, and Lj will map xk in the negation of xk. So this will mean that literal Li for the component Cik will be 0. So in this case, Le of Cik is the conjunction of Cik, so is the negation of Cik. So it's 1 minus Cik, it's 0. So in this case, you'll have that Cik equals 1. And for Hj, you'll have that 1 minus Cik, it's 0, because you have all the terms are 1. So also this one. So 1 minus Cik, it's 0. This will mean that Cik 1 minus, so this will mean, so what I wrote here, so it will be 0, so Cik will be 1, and Lj of Cik will be 1. So this will mean that Cik will be 0, but from the previous point you'll have that Cik equals 1, so you have the contradiction. Okay.
Yes.
Okay, so whenever these two literals are equal, you prove very easily the contradiction. Now, if they have a different form, so either Li of xk equals xk and Lj of xk equals the negation of xk. So now what we're gonna do, we take another point Cm that is different than Ci and Cj. So you'll have that the indices m is different than I and j, and you have one. So m it's between 1 and d plus 1, and it's has a different value than e and j. So you'll have that hi. So hi will map the point Cm to label 1, and hj will map the point Cm in label 1. Okay, because this is how function hi and hj works. So they map the point C. So hi map the point Ci in label 0 and all the other points in label 1, and hj map the points sg in label 0 and all the points into label 1. Okay, and now the contradiction will come easily. So hi it's a conjunction of many terms. So hi applied to Cm, it's a conjunction of many literals, and because you have the final label it's 1, so you'll have that Li applied to your point, to the k component of your point, to Cmk will be 1. So this will mean that Cmk equals 1. But the same stuff will happen to the literal Lj. So Lj applied to Cmk equals 1, but now Lj is the negation of your variable. So you'll have that Lj of Cmk equals 1. This will mean that 1 minus Cmk equals 1, so Cmk will be 0. So Li will say that the k component of Cm is 1, and Lj will say that the k component of your Cm point will be 0. So you arrive at a contradiction. And in the case 4, you have the other way around. So you'll have that Cmk will be 0 from the Li literal, and Cmk will have label 1 from the Lj literal. So in the end, you arrive at a contradiction. Okay.
Yep, I got it.
Okay, so yeah, so it's a very technical proof. Now I'm very glad that I managed to write it step by step. I do believe that on Friday I didn't explain so well this proof. So you could compare this proof with the other one, and I think here it's much clearer. So the basic idea to come up to a contradiction, you have d+1 function, you will have d+1 literals that use only d variables. So there are at least two literals that use the same variable. These literals cannot be one, so they can have two values. You arrive at 4 cases, and then it is quite easy to prove the contradiction. Okay.
Yes.
So any question regarding this stuff?
No, it was pretty clear.
Okay.
I mean,
Okay.
ask the questions.
Do you have other questions? So either related to the third exercise or to the other exercises?
I have a general question regarding finding the VC dimension.
Yeah.
Is it okay if I write an example in LaTeX on my laptop and share my screen?
Yeah, sure.
All right, it will take like 1 or 2 minutes.
Is it related to your homework?
Not that directly related. I mean, I'm not asking if I did something right or wrong.
Okay. So I was asking because I'm intending to put also this recording on Moodle, and if you would have shown me your solution, this would have been a little bit complicated because maybe your colleagues would have seen some solutions. Okay.
All right. Well, in that case, if I'm not sure about, I don't know, an approach in my solutions, can I send you a mail with them?
Yeah, sure. Sure.
Oh, okay.
So, in the general case, when you want to find the VC dimension of a class of functions, so first you have to come up with an example, with a particular example of a subset C that is shattered by your H. So it's just a particular example, okay? So this will be the first point.
Okay, but by particular, we mean literally any point. So
any subset.
Any subset. All right.
Any subset.
So,
okay.
So
here, so for example, in our case, in our third exercise, we took the particular case of C being the set of D points where each point is a unit vector. So it's a particular choice. It's the set of 1, 0, 0, 0, 0, then 0, 1, 0, 0, 0, then 0, 0, 1, 0, 0, and 0, 0, 0, 0, 1 at the end. So you have a very particular C which has D points. So we didn't show that H shatters any set of D points. We have shown that our H shatters a very particular set of D points. So this is the first step. You find a very particular C. Usually these unit vectors work very well. Yeah, I think also. So I think in exercise 2 we show something related for the HD rectangles. We show that it can shatter the set of unit vectors and the set of minus unit vectors. So there you consider points of 1, 0, 0, 0 and minus 1, 0, 0, 0, if I remember well.
Okay.
Yeah. So you can, so depending on your H, so the first step is to find a very particular C of subset containing D points such that H will shatter this C. So this will mean that the BC dimension is greater or equal than D. And the next step, which is the hardest step, to show that any C of D plus 1 points cannot be shattered by H. So in the first step, a particular C can be shattered by H. So if you remember the proof for H rectangles in 2 dimensions, we show that you can have subset of 4 points that cannot be shattered by H. Yeah, but if you consider a set with points that are arranged in the diamond fashion, then this will work fine. So you'll have a particular C that can be shattered by H, but not all set of 4 points can be shattered by H in where H is the set of rectangles in 2 dimensions. If you go back to lecture 5, you will see this very fine distinction between proving the lower bound on the VC dimension, where you have to find the particular subset C, and then proving the general stuff that your H cannot shatter a subset of D plus 1 points. So this is exactly what I did here in exercise 3. So here, if I go back, so first part was that. So the first part was that H shatters set C, where C was a very particular choice. Yeah, so C was this choice, E1, E2, ED. Okay.
Yeah.
And now the second part was the hardest one, and here we assume that there exists a set C of C1, CD plus 1 point. So these points could be anything, and we arrive at the contradiction in the general case.
Yeah.
So these are the 2 main parts. So, but if you have a very particular question about, I know your homework, and this is not such a this question doesn't ask me to solve a little bit of your homework of your assignment 1. Then I will give you an answer by email.
All right. Thank you very much.
Okay. Do you have other questions for exercise 1, 2, 3, or 4?
Can I share my screen a bit?
Yeah.
To post a question.
Yeah.
I think you have to stop sharing for a bit.
Okay.
It's all right. Okay. All right, so this is it.
Yeah.
So we consider the following H. So there are intervals on the real line from 0 to some number greater than 1.
Yeah, R, okay.
R, yeah. And we are trying to find the VC dimension, for example. Now, how particular can we get? Because I could say here that we can get 2 points, like 0.1 and 0.2, both labeled with 0, 0.
Yes, so they will be labeled with 0, okay, yeah.
Which cannot be labeled by 0R with R greater than 1, because 0R would label everything within itself with 1.
This particular H will label all points. So let me look again. So H consists of subsets of the real line 0R, yeah?
Yeah, with R greater than 1.
If a point it's contained in a 0R, so you'll have value 1, okay?
Yeah.
So for the 2 examples that you have shown here, x1 and x2, so now so x1 it's a point, yeah.
Yes.
So if x1 it's 0, 1, yeah.
Yeah.
So if x1 it's 0, 1, so you can have that this point it's labeled will get labeled 0 if r is smaller than 0, 1. If
Yeah.
r is greater than 0, 1, it will take label 1. No?
Yeah.
Okay, so x1, so what you wrote here, x1 and x2, it's in that set. This is not quite okay. So you can say if x1 it's 0, 1,
Yeah.
then you can find a function in H such that it can be labeled with 0, and you also can have a label in H which is labeled with 1.
Okay. But can we also say something like we consider the point 0, 1 labeled with a 0, but given that r has to be greater than 1, our
Yes, but it's labeled but by what function? By a small h, no? In your capital H.
yeah.
So yeah, so you can say, so we consider, so either, so we consider a point x1 that is labeled by a small h, and this will mean, so if h gives label 0 to your point x1, this will mean that r, I don't know, it's smaller than 0.1, no?
Yeah.
And x2 it's labeled by the same h, or
Yes.
by another h.
I think in this case it's irrelevant, since for all h's r
Of
has to
course,
be
of course.
greater than 1. Okay, so we basically say that something like for h in h of x1 would give the label 1.
Uh-huh.
If r smaller than x1, actually.
Yeah. Yeah.
But since by definition our r is greater than 1, we reach a contradiction, and that's how we show that we can't label that point in this case.
So of course that you don't have any h small in capital H that will label 0.1 with label 1. Okay.
Yeah.
Now, but you also have to define what is the domain. So you have, so h, capital H, will consist of function smaller h that will be defined on x2 and map it to 0, 1. So what is x in your case?
X is a X is a point on the real line.
Yeah, but the domain of your function. So h, so smaller h will be defined on capital X to value 0, 1. Yeah.
Yeah.
And your capital X should be, I don't know, it's a real line, it's 0, infinity, it's 0, 1.
Let's say this time it's
could be r.
Let's say it's 0, infinity, because if we had r, we could take any point below 0.
Of course, yeah.
Any 2 points below 0, and they wouldn't be shatterable.
Sure.
Actually, any point.
Yeah.
All right. So for 0, infinity, we'd have.
Yeah, it's fine. So if you take 0 in infinity, it's fine. So you have smaller h is defined as or on 0, infinity, and will map to 0, 1. And h is of the form, it's an indicator function. So h is basically h r, which is the indicator function of the segment 0R. No?
Yeah.
Okay. Yeah, so h of x1 is equals 1. It's if r is smaller or equal with x1. Okay.
Yeah.
Yeah.
But R is greater than 1 by definition.
Yeah.
So, you know, we have a contradiction.
So no, so you just have shown that your h will label all points in 0, 1 with label 0. You just so this is what you proved, but you haven't proved that any. So I guess you want to compute the VC dimension or of your capital H, yeah.
Yeah.
So the first thing is to have that H will shatter a subset C of D points. So if you take like your C to contain, I know, if you take to contain only 0.01, your capital H will not shatter 0.1 because it cannot give label 1. Yeah.
Yeah.
Now, if you take 0.1, 0.5, then your H will shatter 0.1, 1.5.
Yeah.
Because you will have a function that will label 0, and you also have another function that it will give label 1. Okay.
Yeah.
So because if you have H 1.3, this will 1.3 is smaller than 1.5, so this will give label 0. And if you take R equals 3, then it will give label 1. Okay, so you have found a particular H that a particular C containing the point 1.5 that is shattered by H. So
Yes.
you know that the VC dimension is at least 1. Okay.
Yes. Yes.
Now, if you want to prove that the VC dimension is 1, you have to prove that any set C containing any 2 points in 0, infinity cannot be shattered by H.
Wait, any 2 points?
Yeah, so any set C containing two points. This is the definition of the VC dimension. Any 2 points.
Well, in the definition, we would have any 2 points can be shattered, right?
So if you want to show that the VC dimension of your H is 1,
yeah.
So first thing, you have to find a particular set C that you have found that is shattered by H. So this will so if you take capital C equals the point 1.5, H will shatter the point 1.5 because you have two functions that can provide label 0 and label 1 for your point. So H shatters this particular set. So you'll have that VC dimension of your H it's greater or equal with 1. Yeah.
Yeah. Yeah.
Now, if you want to prove that the VC dimension is exactly 1, then you have to prove that the VC dimension is strictly smaller than 2.
Yes, and for this we have to find at least one example.
No, this is what I'm saying. You don't have to find just one example. You have to show that all sets containing 2 points cannot be shattered by H. All set of points, okay?
All right.
Because remember what we did in lecture 5. What we did in lecture 5 with H rectangles in 2 dimensions. Maybe I will share my screen to remind you what we did.
Okay.
So let me open lecture 5. So we go back to this example, yeah?
Yeah.
So we have h of rectangles in 2 dimensions, yeah?
Yes.
And the question was in lecture 5, does this set of function shatters any set A of 4 points in R? And here you can see an example of these 4 points. So you can see an arrangement. So you can see a particular set C containing 4 points that cannot be shattered by your H. But here you see what I wrote here. So if you take A, so yeah, so in this case, instead of the C subset, we work with the A subset. So if you take A, the set of 4 vertices of a rectangle with axis aligned in R2, then HREC2 will not shatter the labeling 0, 1, 0, 1. So if you if you consider the labeling with the opposite vertices having the same values. So does this mean that the VC dimension of our set of functions is strictly smaller than 4? And you see here, no. Yeah. So either we show that all sets of size A are not shattered by HREC2, or either we find a particular set A of size 4 that is shattered. And what we did, we found this particular A.
Yeah.
That A was shattered by HREC2. So back to your case. So if you find 2 points that are not shattered by H, this will not mean that the VC dimension of H it's strictly smaller than 2. You need to show that for each set of 2 points, your H will not shatter C.
So basically, you have to show that H cannot shatter a whole family of points of dimension D.
Yeah, exactly. Well, D plus 1 if you
D plus 1 if you want
that
D, yeah.
the VC dimension is D.
Yeah. So basically, if for example we say that we prove that some H has VC dimension 2.
Yeah.
But we have, let's say, one example or a finite number of examples of size 2 that are not shatterable. That doesn't mean it's not shatterable, right? The whole.
Exactly. So you have to prove that any set C of 2 points cannot be shattered by H. So the second part doesn't work on showing that there are set that are not shattered. You have to show that any it's not shattered. So in the first part, you have to show a positive thing. There is a set that is shattered, and in the second part, all C of D plus 1 points are not shattered. So remember what we did here in lecture 5. Remember what we did in the seminar 3 here with the in exercise 3 with the HD conjunctions, where we first shown in the first part that there exists C containing D particular points that are shattered, yeah, and then all sets of D plus 1 points will not be shattered.
All right, and I got it now.
Okay.
All right. Yeah.
If you have other questions, you can ask me or write me, and I will answer.
Regarding this seminar, let me check a bit. I don't think I have any questions right now. I mean, regarding proofs about Bach learnability, for example, I think I asked this, but we can use, for example, the geometric argument that something is the way it is.
Yeah, yeah.
All right.
Yeah, it's fine. So I will be repeating this seminar because it's very important on Friday. So if you, so maybe, so you can go through the solution again. You'll see that I put a much better solution for the second part, for the second exercise. And if you have question, you can join the meeting on Friday and ask me anything about it.
All right. Thank you.
Okay.
Yeah.
Okay. Cool. So we stop here.
Okay. Thank you.
Bye.
Bye-bye.